Good evening. First of all, I would like to thank the organizers for the opportunity to give a presentation in this meeting. And also I would like to say that in Mathematical Institute, we also have a logical seminar with rather old tradition. And I would like to invite all of you to consider possibility to present your work in our seminar as Professor Speransky already did a month ago or something like that. I also have to say that I caught a cold, but I will try to speak slowly and clearly so that you can follow my presentation. The presentation, the aim is to present our recent work on a combination of formal methods related to reasoning about probabilistic, temporal, and epistemic properties, and to illustrate one of possible applications of that approach. Sorry, for some reason I cannot change my slides. Sorry. Okay. My talk will be mostly based on the following three papers, which are rather long for logical standards, but it is a consequence of the considered very rich formal language and all issues that appear from combinations of different logical frameworks. And my presentation, to be self-contained, also contains a good number of slides, but I will skip some of them to keep a reasonable length of my talk. Here I give some historical references and also a list of more or less recent relevant papers about the topic of my talk. Another remark in this introduction concerns the word logic, which will be mentioned very often. But by that word, I will refer to a formal system which can be used to represent some kind of reasoning in form of exploring consequence relations or derivations of some formulas from the other formulas. To specify logic, we start with definition of symbolic language. Then semantics should be associated to the language, giving meaning to formulas, connectives, and so on. There are notions of models and relations of satisfiability and semantical consequences. Also, inferences can be studied by means of an axiom system, where the notions of proofs and syntactical consequences should be defined. Finally, there is a bridge which connects those semantical and syntactical approaches. It can be established by soundness and completeness theorem, where one can prove that a formula is semantical if and only if is syntactical consequence of a set of formulas. And this is our approach. We define a language suitable for some kind of reasoning and then try to give its model theoretic and proof theoretic characterizations. There are also, of course, other interesting issues related to logics, decidability, for example, and I will mention some of them. This is the plan of my talk. After this introduction, I will mention some basic notions of Kripke models for model logics and present essential ideas about probability logic. Then the main part is about PTEL, our logic for probabilistic temporal and epistemic reasoning. And I conclude with an example to illustrate expressiveness of this logic, namely how to describe and model and analyze a blockchain protocol. I have been told, and I saw from your references, that members of this seminar are very familiar with model logics. So I'm just going to recall some very basic notions to establish common vocabulary, while much more attention will be devoted to the part related to uncertain reasoning based on probability logics. Okay, in the epistemic framework, we have a formal language with propositional letters, set of agents, classical operators, and epistemic operators for knowledge and common knowledge. So that this is one example of formulas. There is also another useful epistemic operator called everybody knows, which is defined as a conjunction of knowledge of all operators. An epistemic model is a tuple where we have a set of non-empty worlds, a set of equivalence relations for every agent, and evaluation. And in the case of a simple model with 7 worlds, that we have an agent A, which from this W1 possible world sees 3 worlds, 4, 5, and 6. Then satisfiability of the formula that A knows beta in W1 is defined such that beta holds in all accessible possible worlds. Next, we can consider a common knowledge formula, in which case we consider so-called reachability relation, which is a union of accessibility relations of all agents. And this is a path of this relation from W2 to W7. And then in the world W2, common knowledge beta holds if beta holds along in all worlds along such reachability path. We will also consider linear temporal logic LTL, where beside the classical operators, we use future operators next and until, and previous and the past operators previous and since, while the other operators once, always in the past, eventually, and always in the future can be defined from the other operators. In the case of LTL, a special kind of Kripke models is used. Here, the set of possible worlds or time instants is isomorphic to the set of natural numbers. Then in R2, the formula next beta holds if beta holds in the next time instant. And an until formula holds in R1 if there is a future time instant, for example, L or 4, and alpha in which beta holds and alpha holds in all intermediate time instants. Situation with past formulas is almost symmetric with an exception that all past formulas, previous formulas hold in the beginning of time. The last part of this combination concerns probability logic, which in this presentation means logic with probability operators. I assume that this kind of logic might be less familiar to participants, so I we'll give some more details of it. Most of the results about probability logics are more or less recent, but the field has much longer history. However, I will skip it for this moment, and if you are interested in if there would be some time at the end of presentation, I will come back to this part. Here, I just mentioned that some of the important names in this field are Leibniz, Bernoulli, Boole, Kolmogorov, Kistler, and so on. So I'm going jumping to the next part, which concerns uncertain reasoning. And we can here consider a few characteristic situations in probabilistic uncertain reasoning. For example, suppose that we have the probabilities of A and B, and the question is, what is the probability of A and B? The picture on the left suggests that only we can say is that the probability of A and B is somewhere between 0 and the minimum of probabilities of A and B, which should suggest that the property of functionality does not hold for probabilities, and that one can employ tools of model logics in formalization. And this is the way, exactly the way we use. Namely, we will talk about logics that enable explicit representation of quantitative probabilities associated with formulas in a model like framework. In a paper from 80s, Nielsen, which this paper actually had a very strong impact on development of logics with probability operators. The author asked for a generalization of classical logic to deal with uncertain knowledge. And he started with a knowledge base from a standard rule-based expert system, and assumed so-called certainty factors, which comes from statistics experience and so on. And the logic he was interested in could be useful, for example, to check consistency of finite sets of such uncertain rules, and to deduce probabilities of conclusions from uncertain premises. That last issue on probabilistic entailment can be illustrated by this example, related to the question how modus ponens can be generalized when one assigns probabilities to A and A implies B. And again, the picture on the left can help us to see what we can do. So if we have no assumption about the distribution, we can give only bounds for the probability of B. It is easy to see by considering this rectangle on the left of the picture. Now, I'm going to give some technical details about our approach to formalization of uncertain reasoning based on probability logics. I will talk about a logic denoted LPP1, which is a propositional logic with probability operators. Regarding the issues about uncertain reasoning, the most general properties of our probability logics are that they allow strict reasoning about probabilities using well-defined syntax and semantics, that formulas remain true or false. They do not have probabilistic numerical true values. So these logics are not multi-valued logics, but more some kind of model logics. In syntax, we use the standard classical language and extend it by a list of unary probability operators of this form with the intended meaning that the probability is at least S, where S is a rational number from the unit interval 0, 1. Then we have the set of propositional probability formulas defined in the standard way. And also other probability operators can be defined from the basic ones. And this is an example of formula in this formal language. The semantics for this formula consists of a special type of Kripke models with possible worlds, where a probability model is a tuple which, besides the set of worlds and evaluation, also contains a function prob, which assigns to every possible world W a probability space. And that space contains a set of worlds, let's say, visible from W, then an algebra of subsets of that set, and a finitely additive probability measure. You can see that in comparison to model logics in this definition, instead of accessibility relations, we have probability spaces which suggest that probabilistic operators in some sense behave like model operators. Actually, we will consider a subclass of these models, so-called measurable models, in which case the set of worlds definable by a formula, or the set of worlds in which a formula holds, is always measurable. And this is a simple example of such a model. For example, we have 6 worlds, and from the world W1, all the measures of the worlds are equal. Then let evaluation be such that P holds in W1 while Q does not, and similarly for the other worlds. Then this blue set is definable by P, and its measure is 5/6. The orange set is definable by Q and with the measure 1/2, and the red set is definable by P and Q, and its measure is 1/3, and so on. In this logic, accessibility relation is defined in more or less standard way, where the key condition is this second one given in red, which says that the probability of alpha is at least S holds in a world if and only if the measure of the set of worlds definable by alpha from that world is at least S. And to continue with the previous example, we can see that, for example, Q does not hold in W1, the same with this conjunction, while the conjunction holds in the worlds 4 and 5. Then we can consider probabilistic formulas, and W1 satisfies that the probability of P is at least 1/2, and the probability of P and Q is 1/3, and similarly this conjunction. It is interesting to notice possible relations between epistemic and temporal modalities and probabilities. For example, if we want that agent's knowledge is about true statement, we can require that knowledge implies probability. Also, probabilities provide a way of gradual measuring of knowledge. Namely, they offer levels of knowledge. That the probability is 1, less than 1, 1/2, 1/3, and so on. And similarly, in the temporal case, we can require something like this formula, which says that if alpha is always true in the future, then in the next moment probability of alpha is equal to 1, or if in a time instant not alpha holds, then in the next time instant the probability of alpha will not decrease. There is another interesting characteristic shared by all three mentioned logics, and it is so-called compactness. We say that the logic is compact if for every set the following holds. A set of formula is satisfiable if and only if every finite subset is also satisfiable. And what is interesting that for all our logics, we can define examples of sets of formulas that do not have this property. For example, let us consider that last one, which says that the probability of P is not 0, but it is less than any rational number from the unit interval. Every finite subset of this set, for example, this one, is satisfiable because we can find a C, an element of the unit interval, such that the probability from a world of the set definable by P is exactly C. But the whole set cannot be satisfied when the considered probabilities are real valued, since satisfiability of this set implies existence of infinitesimals. This failure of compactness have some influence on axiomatization, which will be discussed later. But here I would like to say that we develop a technique for axiomatization of non-compact logics so that we can prove strong completeness, for example, for this LPP1 logic. And similarly for different extensions, for example, logics with other probability operators, with conditional probabilities, qualitative probabilities, confirmations, probabilities with other ranges, finite countable, with infinitesimals, unordered, then probability logics with non-classical Bayes logics, first-order probability logics, and so on. The logic is decidable, and this slide illustrates its decision procedure. It is interesting that the basic ideas of this procedure go back to George Boole in 19th century. So let us consider this probability formula, and then we can represent each classical subformula in the corresponding complete disjunctive normal forms, where these conjunction of literals are called atoms. It is important that atoms are mutually exclusive. Then the formula is satisfiable if and only if the following linear system is solvable, where the first equation says that the sum of the probabilities of all atoms is 1, then that the probabilities of atoms are non-negative, and the last two inequalities correspond to the probabilistic subformulas, where the important thing that thanks to the fact that atoms are mutually exclusive, the probabilities of formulas are the sums of the probabilities of the corresponding atoms. Of course, it is just an example for this formula, but I think that it illustrates the idea behind the procedure. And now I am going to our main topic, to a probabilistic temporal epistemic logic, denoted PTEL. The main goals of our work about PTEL are introduction of syntax and semantics suitable to capture interesting phenomena about uncertain framework of distributed systems with agents, then we are interested in so-called non-rigid sets of agents, which means that an agent can be active in some time instant and inactive in the rest of an execution. Then in providing strongly complete Hilbert-style axiomatization and in analyzing decidability. At the synthetical level, we combine languages of the mentioned logics. So we have the set of agents, the set of agents, the set of propositional letters, and a particular subset of this set where the intuitive meaning of this propositional letter is that agent A is active. Then we have classical temporal epistemic and probabilistic operators with an extension concerning probabilities, where we consider two types of probability operators, expressing that the probability, the first one about the probability of set of runs is at least S, and the second type expressing that the probability of set of possible worlds according to an agent A is at least S. They will be explained shortly. We also use the standard convention for denoting repetition of unary operators. An example well-formed formula in this language is this one, and I'll try to read what it says. Its meaning is that S is the probability of the set of runs satisfying that always holds for every agent A if A knows that the probability of alpha given by the agent B is at least R, then in the next time instant, it is common knowledge among agents that the probability of alpha given by the agent A is at least R. So I think you can feel what we can formulate in this logic. A distributed system is a collection of components, processors, agents, nodes that are located in some space, physical or virtual, that communicate in order to obtain some common goals. And the main problem in reasoning about distributed systems is uncertainty, especially due to the non-delivery of messages, possible errors or unexpected behaviors of agents, lack of global knowledge, and so on. And an usual approach, which is very often used in the description and analysis of distributed systems and protocols, is based on Kripke models that combine probabilistic, temporal, and epistemic properties. Then a point or a possible world or state is a pair where the first component is a run and the second component is a time instant. A point corresponds to one state of the system. Then a run is a complete description of events in the system during one execution of the system. And it consists of a sequence of points, while a distributed system is identified with a set of runs that describe all possible executions. In a distributed system, there are agents, and as I said, it is not necessary that all agents are always active. So, for example, we denote that in this way. In the point RK2, agents A1 and A2 are active, while in the next point A2 and A3 are active. Then modeling knowledge of agents is related to accessibility relations between points. The standard model is that an agent A in a point considers other point accessible if the agent cannot differ from these points. For example, if her local state is the same in all points. For example, here we illustrate that the agent A1 is active in RK4, and that beside that point, the other 3 points are also accessible from RK4. Note that accessible points belong to different runs. Here, we should notice the following thing. If an agent A is not active in point Rn, there appears a situation called, in the terminology of model logic community, dead-end worlds. It means that according to the agent A, no other points are accessible from Rn. In that case, by the definition, A knows all formulas, including the false ones, which corresponds to beliefs. Of course, it is possible to consider only models without dead ends, where agents are active in all points, but this approach is more convenient for our purposes. And as a consequence, the requirements for accessibility relations are symmetry and transitivity. And if A is active in a point, then also reflexivity. In that case, of course, A knows only true formulas. Concerning measurable sets of objects, those sets are definable by formulas, and objects, elements of those sets, can be runs or points. It is possible to distinguish between two different kinds of probabilities. Local probabilities given by agents involved in execution of a system, and a global probability given by an observer or a system designer independent of agents. In the literature, there is no unique approach who can measure those sets, and the choice of measurable sets also. So we have decided that sets of runs are measured by a global observer, where a set of runs definable by a formula contains all runs where alpha holds in the initial point of the run, while sets of points are measured locally by agents. Graphically, in that point R05, let the red set be defined by the formula gamma. Then the agent A2 gives here probability in that point to the set definable by gamma. Another type of measurable sets of objects, sets of runs, is more complicated to graphically represent, so I avoid that here. To conclude, a PTEL model at the intuitive level, a PTEL model consists of a set of runs, where a run is an infinite sequence of points which represent a possible execution of a system. Each run has the starting point, and its time flow is morphic to the set of non-negative integers. Then, to every point are associated a set of propositional letters that holds in the point, a set of agents that are active in the point, a set of relations that describe accessible points, and a set of probabilities that measure sets of points and sets of runs. This definition can be, of course, given formally in these two slides, but I will skip that and go to satisfiability relation. definition of satisfiability relation combines the corresponding definitions for epistemic, temporal, and probability logic. So I will skip almost all of them and go directly to probability part. Where the important thing is again that the set of objects definable by formulas must be measurable, and I repeat that we consider measurable PTEL models where we can speak about probabilistic formulas without restrictions. So, for example, to obtain that this probabilistic formula that according to the agent I, the probability of beta is at least S in the point R05. We consider this red set definable of points definable by the formula beta, and consider the probability in the point R05 according to the agent A, which should be at least S. And the similar constraint holds for probabilities of runs. Definition of valid formulas and semantical consequences are standard. Particularly, a formula alpha is a semantical consequence of the set T of formulas. If for every point, if the point satisfies all formulas from the set, then it also satisfies the formula alpha. In this framework, the main logical issues concern providing a sound and complete axiomatization and decidability, where in fact there are two kinds of completeness theorems. The simple ones, one which says that a formula is valid if and only if it is a theorem, and extended or strong completeness, which says that a formula is a semantical consequence if and only if it is syntactical consequence of a set of formulas. And also there is that property which I mentioned already, compactness. Okay. I emphasize that probability and recall that there are already mentioned sets as examples for which compactness does not hold. It is somehow not pleasant from the logical point of view. Namely, finitary axiomatization with strong completeness imply compactness, which means that for PTEL, since compactness does not hold, there is no finitary or recursive axiomatization for which we can prove the extended completeness theorem. With finitary axiomatization, we can only have the simple completeness. But then we have a logical problem. There are consistent sets, for example, the mentioned ones, that are not satisfiable, but that are consistent, which means that syntax and semantics do not match. In the first order case, the situation is even worse. It was proved that in the general case, there is no sound and complete recursive axiomatization for first order temporal or epistemic or probabilistic logics. But we will not go into details here, except to say that this approach that I am going to present solves these issues. Here, we provide an infinitary axiomatization such that infiniteness is present only at the meta level. Namely, formulas are finite, as you saw already, but there are inference rules with countable many premises and one conclusion, so that proofs are allowed to be infinite. There is a technical, for this logic PTEL, there is a technical definition of nested implications, which addresses combinations of different kinds of model operators and is used in formalization of infinitary inference rules. However, I will not go into its complicated conditions, and I give here just an example of such formulas where you can see how formulas with leading model operators are nested in an implicative formula. The axiom, this in the next few slides contain the axiomatic system for PTEL. It is a combination of standard axiomatizations for classical propositional, then temporal, epistemic, and probabilistic logic, with addition of infinitary rules. I will go through these slides quickly and just mention several things. For example, we have instances of classical tautologies and the modus ponens rule. In the case of temporal axioms and rules, we have necessitation for next and the previous operator, and two infinitary rules which that concern until and since operator. In the case of epistemic parts, we adapted axioms to the case of non-rigid agents, and also have knowledge necessitation, and this infinitary rule which corresponds to common knowledge. Then this is the part of probability axioms that corresponds to probability on runs. The first axiom says that each formula is satisfied in set of runs of the measure at least 0. Then the next two formulas two axioms correspond to ordering, and the axioms 4 and 5 correspond to additive probability. We have also the rule of probabilistic necessitation, and this infinitary rule, which corresponds to probability, which we call Archimedean rule. And the part of the axioms that corresponds to probabilities of points is very similar. In the axiom system, there are several infinitary rules with countable set of assumptions and one conclusion. They are given in the form of nested implications, which allows that rules can be applied to inner part of formulas. However, if for the moment we ignore that nesting, this rule, Archimedean rule for probability, can be represented in much simpler form, where you can see that the rule actually says if the probability of alpha is arbitrarily close to R, then it is at least R. And this rule can be also represented in a tree form, where the conclusion has infinitely many processors. And the similarly holds for all other infinitary rules, but I have to emphasize that we need that complicated form of infinitary rules to prove completeness. The notion of notions of proofs and syntactical consequences are also defined in the standard way, except that proofs can be countably infinite, and that premises of necessitation rules must be theorems. Here we can see that in our axiom system, we can prove inconsistency of this problematic set. we can see proofs in both forms in as a sequence and as a tree. So at the beginning, we have all elements of the set as consequences. Then we can apply the infinitary rule and obtain that the probability of P is equal to 0. And then from these two formulas, we can entail a contradiction. Recall that this can be proved only in the case of infinitary logic or logic with infinitary rules, and it cannot be proved by a finitary system, since in that case all proofs are finite, and every finite subset of this set is satisfiable, so it cannot imply a contradiction. In the proof of completeness theorem, we have a mix of Hankin-style procedures for proving completeness for classical and model logics, where the key points correspond to handling of infinitary rules. The completeness proof consists of several steps. We start with the form of a deduction theorem, as it is usual in classical, but not in model logics. Next, we prove Lindenbaum's theorem, which shows how to extend a constant set of formulas to a maximal constant set, and also the so-called strong necessitation theorem, which allows us to put model operators on both sides of consequence relation. Then, the canonical model is constructed using maximal constant sets of formulas, and we prove that a formula is satisfied in a point of the canonical model if and only if it belongs to the maximal constant set of formulas which corresponds to the considered point, and also that a set of formulas is consistent if and only if it is satisfiable, which is actually the strong completeness theorem. I'm not going here in this part, but the key part of handling infinitary rules is actually in the Lindenbaum's theorem, which somehow differs from the standard proof. The satisfiability problem for this logic, denoted P set, is for a given formula, are there a model and a point in which satisfies the formula? The stability of parts and combinations of parts of PTEL are discussed and proved in several papers in the last 40 years. But some characteristics of the language and models for PTEL do not allow that techniques for proving the stability to be applied to PTEL in a straightforward way. At least we could not see how to do that directly. Particularly, the language of PTEL contains probabilistic and past-time operators, and the procedure from one of the mentioned papers is not applicable. Then, since models for LTL, linear temporal logic, are infinite, PTEL does not have the finite model property, and the filtration technique for model logic is not applicable. Also, the stability procedure for LTL cannot be applied directly because we have to guarantee that some sets of positive measures, after erasing points, you will see that, would not become empty. Decision procedure for PSAT is based on two main properties. PTEL satisfiability of formula can be reduced to checking satisfiability in a class of finitely representable structures. And second, the size of any such structure is bounded by a recursive function of the size of the formula, so that satisfiability of formula can be tested in a finite number of steps. This is illustrated in this, the idea is illustrated in this picture, where the model on the left is unrestricted in the size starting model, and the model on the right contains a finite number of runs, each of them with a finite number of different points, and this last part which repeats and in that way generates an infinite tail of the run. This reduction can be realized in a number of using a number of transformations, and I'm going to illustrate those steps. At the beginning, some auxiliary notions. Let us consider a formula alpha. Recall that we have propositional letters of this form, which says that an agent is active. Then we have the set of all subformulas of alpha and the union of these two sets. Then we have atoms, where an atom is a conjunction of possibly negated elements of that union. And again, similarly as for the probability logic LPP2, it is important to note that in each point, exactly one atom holds, while different atoms are mutually exclusive. This is the first transformation of models. Here we concern extensions of accessibility relations. The idea is that later, when some points are deleted, we have to guarantee that some sets of points remain non-empty. For example, the sets with positive measures cannot become empty. Here we connect these red points in which the same atom holds, and generate transitive and symmetric closure of accessibility relation. And the same for all other points in which the same atom holds. At the end, all points satisfying the same atom have the same set of accessibility points. And what we can prove is that this transformation does not change the stability of subformulas of alpha. Then we can delete some points. Let us consider these two red points which satisfy the same atom, and suppose that for every point between them, there is another point outside that interval which satisfies the same atom as that considered point. In that case, we can delete that interval, all points from I plus 1 to j, and in that way the run is compressed so that the remaining points coincide, namely points before the point I remain the same, the point j plus 1 becomes I plus 1, and so on. Again, we can prove that this transformation has no impact on satisfiability of subformulas. After relating all suitable points, we proceed by constructing so-called periodic runs. On a run, we find 2 points that satisfy the same atom, such that if an atom holds in any point of R, it must hold before Rj. And also, if until formula gamma 1 until gamma 2 holds in Ri, then there is a point L between I and J, such that gamma 2 holds in the point RR, L, and gamma 1 holds in all points between Ri and Rl. Then we can delete all points after j minus 1. First of all, we have to prove that such points Ri and Rj always exist on every run, and then we can delete points after j minus 1 and make a loop that return from j minus 1 to Ri. The first part then is called index, and the second period. By repeating the period, we obtain an infinite run which finitely representable. Again, we can prove that this transformation does not impact satisfiability of subformulas. So, by repeating the previous step, we can start from unrestricted model and obtain a model in which all runs are periodic. Moreover, satisfiability of subformulas of alpha is not changed, and all points that satisfy the same atom have the same accessibility relation. Note that in such a periodic structure, there actually are only finitely many different runs. Namely, we can define an equivalence relation, tilde, on the set of runs, such that the starting indices and periods for two runs in relation are equal, and that the corresponding points of these two runs satisfy the same atom, the sets of active agents and accessibility relations in those points coincide. This is an equivalence relation, and from each equivalence class we can choose one representative run. In that way, a finite representative model can be formed. And again, this transformation does not change the stability of subformulas of alpha. Then we can proceed to the stability theorem, where the proof idea is to determine a finite number of the finite bound of the number of points in the periodic model, where for each run the number of points is the sum of the corresponding index and period. Then analyze all periodic structures with the number of points limited by that bound, and show that it is possible to check satisfiability of the considered formula alpha in every of such periodic structures in a finite number of steps. So in this way, we obtain decidability, and then by analyzing the bounds of sizes of the numbers of runs, points, and so on, it is possible to give this upper bound for complexity. The last part of my presentation refers to the application of PTEL to modeling of an analysis of blockchain protocol, and I will try to give you a feeling how we do that. In general, there are two types of organization of systems, the centralized one and the distributed, in which components communicate without centralized coordination and control. And blockchain is an example of protocols for such distributed systems. The protocol is used to achieve consensus in a distributed environments. For example, it is the base for Bitcoin cryptocurrency, and it was defined in that paper by Nakamoto, where it is assumed that there is a network of agents called nodes in terminology of blockchain, which communicates. And the idea is to organize data in blocks and to add blocks in a change-sensitive manner at the end of a decentralized, distributed, and public digital ledger called blockchain or chain. Then to achieve consensus about the accepted blocks, the nodes in the network create so-called proofs of work. They try to solve a hard puzzle related to this new block. And the first node with a valid solution accepted by majority of nodes is the winner, and its block is added to local ledgers. The ledger represents the complete history of all approved transactions. These steps are illustrated in the following slides. From the point of one node, it keeps its local ledger, for example, this unique block. In a round of execution of the protocol, the node collects new data and tries to solve the corresponding puzzle. If it solves the puzzle, the solution is distributed to other nodes. Other nodes check if the solution is correct, and if it is correct, they added the block to their local ledgers. However, it is possible that two nodes broadcast different versions of the next block simultaneously. For example, these blocks C and D. And some nodes receive one or the other first. In that case, they work on the first node they received. And this situation is called a fork. Forks are resolved in later rounds when a new proof of work is found and one of existing branches becomes longer. Then the nodes that were working on the other shorter branches switch to the longest one, which in this case is A, B, C, F, and G. There are several sources of uncertainty in blockchain protocol. For example, with some probability, more than one node can produce new blocks. In which case, with some probability, some nodes receive one or the other block first. With some probability, agents is not active, and so on. So an execution of a blockchain is a probabilistic process. Consistency in that framework means that nodes establish a consensus on long enough part of the ledger, where consensus is represented by common knowledge among nodes. More formally, so-called T-consistency says that for every positive integer T, in each round of an execution of the protocol with high probability as a function of T, the prefixes of nodes ledgers, all except the last T blocks, coincide and remain in the ledger forever. So our plan is that in PTEL language, we can formulate basic properties of blockchain as new axioms and also T-consistency, and to show that from PTEL and these new axioms, we can obtain that consistency which we are looking for. To give you a feeling how it works, I show some slides. First, some auxiliary notions. For example, this POV A means that node A produces a POV. ACC AB means that the node A accepts the proof of work produced by the node B, and so on. Then we have axioms that correspond to basic properties of blockchain. For example, the first one says that in each round, at least one agent produces proof of work, or this one, axiom 6, gives an upper bound that more than one agent produce proofs of work. Then the next block of the axioms, for example, that last one, guarantees that once established consensus on the ledgers never changes. To this extended set of PTEL axioms correspond a subclass of PTEL models for which we can prove strong completeness. And also, we can prove some auxiliary lemmas. For example, the first one says that at least one node is active in each round, and the second one that there cannot be an agreement of acceptance of two different proofs of work. All these statements lead to the main consistency theorem, which states that it is common knowledge among nodes that with high probability long prefixes of their ledgers coincide, and that probability exponentially tends to 1 as the length of the ledger increases. So, to conclude, I have presented a logic which formalizes probability temporal epistemic reasoning, show you axiomatization and strong completeness and decidability of that logic, and illustrate how PTEL can be applied to model and analyze a distributed protocol blockchain. Note here that we do not analyze how a proof of work is produced, which means that the same technique and the same statement holds for other statement holds for other types of consensus. Furthermore, we can consider to use conditional probabilities instead of classical implications, which in some cases is more suitable, or also using probabilities with non-standard ranges, ranges with infinitesimals instead of real valued probabilities. Okay, thank you very much for your attention.